This is triangle ABC, and it's a 3, 4, 5 triangle, so that's a right angle at vertex A. Now, suppose that on BC, we choose 2 points, P and Q, and on each of AB and AC, we choose 1 point, that would be R and S, such that the 4 additional points form a rectangle. Now, I want to ask you, what is the maximum possible area for rectangle PQRS? Don't you just love optimization problems in geometry? So let's delve right into it. Firstly, I think it's a good idea to kind of redefine this rectangle. I mean, like 2 points on BC and 1 point on each of, that's a little bit too complicated. So is there a way we can, shift our focus to think about this rectangle in a different way? Well, I'm going to draw our model again, okay? Now, notice that this rectangle that we're interested in is literally defined just based off of RS. Why? Because since RS is parallel to BC, then notice that once we have RS, we just need to draw the fixed corresponding perpendicular lines down to BC, and we have a rectangle. So it basically fixes the rectangle that way. So therefore, this rectangle is defined just based off the length of RS. So let's call the length of RS x. Now, the other dimension of the rectangle, we don't really have a good way to kind of represent that in terms of x, so we'll just call it y. However, here's the thing. If we can ever write y in terms of x, that would be perfect, because then we have a function about x, and we can just find the maximum from there. So how do we proceed? Well, looking at this diagram, there doesn't seem to be a straightforward theorem we can apply. But here's the thing. Whenever you see that a configuration forms smaller triangles from a much larger triangle, then it's usually time to think about similar triangles. Check this out. Okay, actually, before we check that out, we're going to find one length. Okay, one length before we use similar triangles. Alright, so this is the length that I'm interested in. Consider the altitude from A down to BC. Okay, the altitude from A to BC. I'll call the intersection with BC point D, and I'll call the intersection of this altitude with RS, I'll call it point E. Now, here is the thing. We can actually get the length of AD. How do we do that? Well, AD is an altitude, as I said, so here's the idea. Whenever you are trying to find the length of an altitude of a triangle, it's usually a good idea to consider area. And the reason is because you can often write the area of a triangle in 2 different ways. Sometimes you can write it in multiple ways to get a system of equations. In this case, there are 2 ways we can write the area of this triangle. One way is 3 times 4 divided by 2, because there's a right angle in between. So one way to write the area of triangle ABC is 3 times 4 divided by 2. And the other way, notice, is the altitude AD times BC, which is just 5, and then divided by 2. They have to be the same thing because they're both the area of the same triangle. So now you can solve for AD. If you actually solve for AD, you would actually get that AD is equal to 12 over 5. And there we go, we've got our altitude. So AD we have. Now, how does this help us at all? Well, as I said, similar triangles. In this case, there is one pair of similar triangle that will literally destroy the entire problem. It will get us to the answer almost immediately. And this is the pair that I'm looking for. This pair is triangle ARS. This is similar to triangle ABC. They are similar, and it's kind of obvious why. Since RS is parallel to BC, the corresponding angles will be equal. So they're similar. Now, because they are similar, we can set up the proportions for the side lengths. But what should we use? I mean, we don't know what AR is. We don't know what AS is. So what do we do? Well, here's the thing. We just got the altitude of the larger triangle ABC, right? And because these 2 triangles are similar, we can also compare their altitudes. Now, notice that in triangle ARS, the altitude we're going to be focusing on is the length AE, right? This is one altitude of triangle ARS, AE, right? So we're going to compare AE with the entire altitude, which is just 12 over 5. We got that, right? That's AD. So that's 12 over 5. Now, this would be equal to, we just choose some other length. Well, in this case, we can literally choose x, right? And then compare, sorry, I'm going to write it down. So we can choose x, right? Compared to the entire base length of BC. That would be 5. And there we have it. But wait a minute, what is AE? What is AE even? Well, notice that because AE, notice that this part is just a portion of the entire altitude, AD, right? Notice that we can literally write AE as the entire altitude, 12 over 5, and then minus y, right? Because this part is literally just y as well. So there you go. And now we can make the substitution. So AE is just equal to 12 over 5 and then minus y. And there we have it. We finally have a way to express y in terms of x. We can just cross multiply and get our, desired results. So we can cross multiply. This would be 12 minus 5y. That's going to be equal to 12 over 5x. Now, admittedly, it would be easier to kind of just, isolate for x, but I mean, I said we would do it for y, so let's just do it for y. So okay, so I've isolated for y. Now we can just use this to write the area of this rectangle, right? So let me first erase all of this because it's taking up a lot of space. Okay, so let's continue from here. We can write the area of this rectangle in terms of x. Firstly, the area is x times y, and this y is equal to this, so we can just make that substitution. So this is equal to x times this, negative 12 over 25 x, and then plus 12 over 5. And would you look at this? This is a quadratic in terms of x. And I'm sure we're aware of how to maximize a quadratic polynomial. I'm just going to go with completing the square. So if we complete the square, transforming this to vertex form, this would be negative 12 over 25 times x minus 5 over 2 all squared, and then plus 3. Hopefully we're aware of how to complete the square. So this is showing us that the maximum value is 3, and it's achieved at x is equal to 5 over 2, which is possible because rs equal to 5 over 2 is clearly smaller than this 5 over here. So it's achievable. So this is the maximum area. So this is equal to 3. And that's our answer. Now, notice that the key idea was that when we saw a configuration that formed a smaller triangle from a much larger triangle, that allowed us to use similarity to get a side length. So yeah, I hope you found this video interesting. I hope you enjoyed it. If you did, please do consider dropping a like and subscribing. Thank you very much. Bye.